Hello, pre-calc students. This is Mr. Beck, and this will be the first set of videos into the mindset of what I am thinking as I'm going through my notes. And as I take a look at the notes here, our first set of notes is from sections 1.1 and 1.2. 1.1 from our book is the distance and midpoint formulas, and then 1.2 is all about symmetry. So in terms of distance and midpoint formulas, what I have highlighted here in red is our distance formula, which you're familiar with. The distance formula comes from 2 points, x1, y1, and x2, y2, which if you establish on a graph those 2 points, what we're doing with the distance formula is we're breaking it up into a horizontal and a vertical component, and then we're really just using Pythagorean theorem. So distance formula they have for problem, for this understanding aspect of it, is we are using these 2 points. Let me go ahead and change color. So our first point and our second point, and we have the distance, which would be x2 minus x1, which if you look at the way that I have this set up, this is x2, y2 here. This is x1, y1 right here. I typically just take first point minus second point. It doesn't matter the order as long as you just maintain that order. So 1 minus 7 squared plus 6 minus 2 squared. So fill in the distance formula and we get to 2 squared root of 13. So what I had on these notes is I had you plot the point C, and that point C is really what's establishing that we're going our base, we're going our height, and we're establishing Pythagorean theorem. So we know Pythagorean theorem is going to be, most commonly seen as a squared plus b squared equals c squared. More appropriately, it's going to be leg squared plus leg squared equals hypotenuse squared. And so the distance formula really comes from the Pythagorean theorem. And then in my notes, we use the midpoint formula. Once again, x1 plus x2 over 2, y2 plus y1 plus y2 over 2. And those, again, very common sense, just fill in the points that you know and come up with the actual coordinate. Now, the idea that I had here on part F was I asked if you have 1 pencil, your friend has 7, together you have 8, and so on average you each have 4. Now, we know that that average is way off, but the midpoint formula is really saying what is the average of both the x and the y coordinate. So on the first set of problems, fairly straightforward. That's what our level 1 problems are. They're designed to be, can you apply the skill? So on 1A, we have our 2 points, x2 minus x1 squared plus y2 minus y1 squared. Now in the end, we end up with 5 square root of 5. So the only difference in, or the only extra step that we have to take here is, do you remember how to rationalize? And to rationalize, I break this up into the square root of 25 times the square root of 5. And we know that the square root of 25 is 5 times the square root of 5. Our midpoint is pretty straightforward. We end up with a fraction, and that fraction is okay, mainly because there's not really a whole lot of work that we have to do. We do end up with a fraction though. For 1b, once again, straightforward, we have the square root of 25 and 29 as our result. That's square root of 29. We know that 29 cannot reduce anymore because 29 is prime. It can only be broken into factors 1 and 29. So therefore, we're going to leave our answer as the square root of 29. Midpoint, in essence, I don't think there are many issues with that midpoint. So for our level 2 problem, suddenly we're now moving away from just having strict numbers into the problem. We now have them as variables. So we have a point A, which we're going to call A comma 0. And that point A comma 0 means that we know the y coordinate is always going to be 0. The x coordinate can change, and we're going to come up with a distance formula that's based off of how those change. This is setting up function mentality, but really we're stressing that we know that those numbers change. And in terms of programming, anytime we do computer programming, a lot of times you take the input in a computer programming, and from that input, you want to use the input to do something else. And really, we're saying whatever this input happens to be, we're then going to say we're going to square it. Whatever this input is, we're going to go ahead and square it, and then we're going to come up with a situation where we're going to have it simplified. Now, common error time, common error. Please know that when you are taking the square root of a squared plus b squared, that is as far as you could take it. This is our end result. A lot of students like to break this up into a plus b. Not correct, mainly because the square root simplifies or the square root's a power, and that exponent simplifies other exponents, and it simplifies multiplication. When you're talking about the square root of addition, that square root does not act on addition. In essence, for those pure math people, the square root does not the distribution process doesn't work from exponents to addition. That's the pure math people. So anyway, we can see this with numbers, that if we take the square root of 16 plus 9, it should be the square root of 25, which is 5. And if we try to do those individually, we don't get the same value. So kind of like, what's your real world check? I always talk about the Triforce, and the Triforce is about looking at things algebraically, numerically, and graphically, which is what my notes go through. And with those, with looking at this numerically, we see that the numbers don't actually work, so they're not the same. This is not a plus b. Midpoint, a over 2 comma b over 2. For part B, what I like about part B, and this problem is set up intentionally, that we end up with this solution of the square root of 25a squared. A lot of students like to say, oh, that's just 5a. One of the things that we have to be very, very careful of is the square root of a squared is not just a. The square root of a squared is not just a. The reason for that is what happens if a is negative 4. We know that negative 4 squared is 16. So the square root of negative 4 squared is the square root of 16, which is 4. Now, if we said, and I'm going to write this as if a equals negative 4, then the square root of a squared is positive 4, not negative 4. So in the end, a, which is negative 4, is not the answer we got. A is positive 4. So that whole statement doesn't make sense whatsoever, which is why we have to say, oh, it's not just a, it's the absolute value of a. What's the absolute value of a? It is 4, which is why that works. I really like to show this a little bit more on a geometric side. And that geometric side is, if I take the square root of x squared, we can see that this graph is the absolute value of x. And I could show that by, let's go ahead and put that function in there. Absolute value of x. No, it's here somewhere. Not seeing, maybe it's right. Yeah, wherever it is in GeoGebra. I know that, or in Desmos. It's not here, so looking funny, whatever. It's the absolute value of x graph. So going back to my notes, that this square root of 25a squared really is 5 times the absolute value of a. That's a little detail that we're going to look at a little bit more on the pre-calc level. We'll see this occur in just random places throughout this. Our level 3 problem, now we're starting dealing with fractions. Fractions are something that I encourage and challenge you to push yourself through, because work with fractions now, the more that you can do, the stronger you're going to be in the future. So for this first problem, the distance, I did set this up. Still is going to be x2 minus x1 squared and y2 minus y1 squared. The reason why this is a level 3 problem is now we're going to have to do a little bit more arithmetic. We're going to have to combine some of those previous skills that you've learned in other math courses. We're just kind of rehashing those. We're building it in, just relearning. And I mean, we don't use these on a daily basis, so there's nothing wrong with not knowing them immediately. Something that I do want to point out is I did leave this written as negative 4 over 2 squared. And the reason for that is because I'm kind of mentally seeing that I have 3 halves squared from this problem, negative 4 over 2 squared. So why did I leave it that way? Just because I knew that I was going to need to have a common denominator, which is what was going on right here. Midpoint, same thing. Most students don't really have an issue and they can follow along with what's going on. Please see me if you have any questions over any of that first page. It's really the second page that, we're going to start getting into some of the thought processes I want to make sure that you're thinking about. So problem number one, we're talking here, it says we have 2 points. We are going to shift those 2 points, and we want to make sure that those 2 points, by shifting them, have the same distance away. In geometry, this is really called translating. So translating, we have 2 points which would form a distance. Suppose I say the square root of 10. With those 2 points, if we shift those points left 9 and down 2, as long as we translate both of those points in the same way, we're not really going to change the distance. and I'm not sure why I put the square root of 10. It's just 10. So we have these 2 points, and I showed that the distance between those 2 points was actually 10. The square root of 100 is 10. When I shifted the 2 points, I created, and what I called those is the new points A prime and B prime. Kind of like numerically, by shifting left 9, what I'm going to do is I'm going to take my -6 and go left 9 by subtracting. That's how I find A prime. And then, or the x coordinate of A prime. And then the y coordinate of A prime, I start with -2 and I shift down 2, which means I'm going to subtract. And that's how I get that new coordinate of -15, -4. And then the distance between those 2 points, once I find them, shows me that, once again, I have the square root of 100, which is 10. For question number two, we can approach this in 2 different ways. Anytime that I approach problems, what I like to see is I like to see one approach, or at least I like to say, I'm going to take this approach to the problem, figure out if I can come up with a solution for that. And then once I'm done with that, then I like to have this personal check of, am I on the right track? So let's temporarily ignore the graph that I have there. And let's look at, if I know that I have a midpoint of 2, -3, or 2, 3, and I know I have an endpoint, what I could do is I can try to take this coordinate of B, which I'm just generically going to say x, y, and I can say, all right, -1 plus x, let me point it out, -1 plus x, meaning, let's use the midpoint, this -1, this x, divided by 2, find the average between those 2 points, and I know that that should equal to 2. The average of my y coordinates, 8 and y, divided by 2, is going to give me 3. So, and then from there, I could set this equal to 2, which I did over here. And then I could set this expression equal to 3, which is what I did here. And I could solve as 5, -2. That's where this is a very strict algebraic approach to it. I like it. There's nothing wrong with that. I do have some students who like to say, does that make sense? And this is kind of like my mental check for the problem, that if I have -1, 8, which is approximately right here, and the midpoint is 2, 3, that distance right there is half of it. So if I go the other distance, it's going to put me at a point in quadrant 4. So when I look at my answer of 5, -2, is my answer of 5, -2 in quadrant 4? Yes. So I kind of feel like I'm on the right track. And how do I actually know if I'm on the right track or not? This is the geometric approach. If I start at point A, which is with the y coordinate of 8, and if I go to the y coordinate of 3, then that means I'm dropping 5. If I go from the x coordinate of -1 to the x coordinate of 2, that means I'm going over a positive 3. So I could do that exact same approach to come up with my other point. For my midpoint, I drop down 5 and go over 3. So 2 different styles of approaches to how I thought through the problem. Both of those are valid. One of the things I am going to encourage from you guys is I would like to see a valid mathematical approach. Just plugging in numbers, randomly guessing, yes, that is a valid approach too. That's going to only take you so far. Having some kind of algebraic thought tends to be stronger, or geometric thought tends to be stronger. That's one of the reasons why we push both algebra and geometry as lessons. We want you to be able to think in both of those ways. We know that you can randomly guess numbers, but when it comes to fractions, most students don't know how to randomly guess fractions that are going to work, because it's not a very easy skill to do. On this second problem, I want to look at the overall question. We can see that question a little bit better for 3A, where it says find all points having this certain y coordinate whose distance from a set point is one number. So that's really what this problem is asking. I want to find all points. Let me highlight this. I want to find all points along the line whose distance from the point 3, 1 is 5 units. So I want to know all points along this line whose distance from this point is 5 units away. So that distance is 5 and this distance is 5. Now with this problem, what I was trying to get at is this idea of Pythagorean triples can be used geometrically to establish what those values should be. If I know that I go straight down 4 units, then this creates a 3, 4, 5 Pythagorean triple. And that 3, 4, 5 Pythagorean triple says, okay, from this x value right here, If I go 3 units in that direction and 3 units in that direction, I should be able to come up with my answer. Most students are not going to think in this manner, and that is completely okay. The whole point is, let's kind of push some kind of different thought in your mind so that you can see more of a geometric approach. Most students would go directly to this algebraic approach that I have to the left, but you can go to a geometric approach as well. Try to think in different manners, because that strength of thinking is what we're looking for in our pre-calculus course. Can you be flexible in your thought to say, let's try this? If it works, great. If not, let's try something else. If that works, great. If not, let's try something else. This problem-solving mentality is what we are hoping for out of our students, because that is really the marketable skill that anybody is looking for in the future. And people don't necessarily want to know, can you do this specific skill? They want to know, can you problem solve your way? Because that ingenuity, that creativity is crucial. It's crucial for growth. So with that said, let's go ahead and look through the algebra behind this. I put on here that any point along the line y equals -3, we can write as the coordinate x comma -3. This turns it into a little bit stronger of an algebraic approach that we say, all right, x -3, meaning the x can change, but we know that the y value is strictly -3. That -3, once again, comes from this -3, that -3. And so now, by turning it into a coordinate, I now have two coordinates, x -3 and 3, 1, that I can apply the distance formula to. And then the rest is working through the arithmetic behind it. So most students, once they get to this point, I have a lot of students who like to multiply the x -3 out, whether it's there or whether it's there. So if you multiply that x -3 out, that is okay. What ends up happening is you have 25 equals x squared minus 6x plus 9, because we know that we have to FOIL that out as x plus 3, or x minus 3 times x minus 3. And then we could bring everything to one side, because that's what we do with quadratics. Factor out the x, and we get our two solutions of x equals 0 and x equals 6. So that's definitely, that is a valid approach. Sometimes that's not quite as easy. In fact, with the problem 3a, I would definitely not take this approach, because that's going to involve using the quadratic formula to solve. Now, can you do that? Absolutely. I'd rather you try to say what is a little bit more efficient at times, and that's where this approach of solving by the square root method. So by the square root method, if we're already set up that way, please utilize that. And we can see that as we get into problem 3a, that once we get to this point, I would rather solve this by the square root method than go ahead and take this to a factored form. That factored form would be, not sure why that jumped, but that factored form would be x squared plus 2x minus 224 equals 0. Now, I'm not sure how many of you know that factors of 224 are. Those factors apparently are 16 and 14. Put it in the right order, we're going to get our overall solutions. I would rather not do that, and I know a lot of students don't want to do that either, which is why the square root method tends to be more efficient. For problem 3b, our question says, we're given 3 points, which I'm going to label as A, B, and C in this way. They don't necessarily have to be in that order, but I'm just going to label them in that order. I want to classify the triangle as equilateral, isosceles, and scaling. So what's the definition of equilateral, isosceles, and scaling? If you don't know, feel free to ask Siri, ask Google, ask Alexa, or ask anybody on the internet. Hopefully they're going to tell you the right answer, or the right definition of it. Equilateral means all 3 sides are the same. Isosceles means 2 sides are the same. And scaling means no sides are the same. So if I want to know what the lengths of each one of these are, that's where I'm going to use the distance formula. And that distance formula, when I do it over here, I get 53. Let me change that because I realize it's wrong. The second one, I do have the square root of 53. And then this one becomes the square root of 106. I'm not sure where the 126 came from. But, so the fact that both of these are the square root of 53 means I know I have an isosceles triangle. And then how do I determine if this triangle is a right triangle or not? In class, I did have a student who graphed this and said, let's take a look at the slopes and see if those slopes are perpendicular. Great approach, I like that. Because this section is dealing with like distance formula and Pythagorean theorem and kind of relating the two, that's why I chose this approach to say, let's use Pythagorean theorem to see if that actually works out. And as it turns out, it does. For for our level 4 problem here, this level 4 problem is kind of a big setup for when you want to move on to calculus. We do see this happen quite a bit, where we need to come up with expressions, and those expressions are in terms of a variable, and then we use that variable and we do something with it. Mainly we do like differentiation and integration and stuff like that. That's next year. What we care about now is, can we set up the expression? So this level 4 problem is really an important piece to this section, because can you set up an equation that is going to, or an expression that is going to allow us to figure out what that distance is based off of any time? So I know the problem is kind of messed up, and I apologize. I'm not sure how that translated incorrectly. But if we have a car that stopped at an intersection, a balloon floats overhead at an average speed of 15 miles per hour at a constant altitude, can we find the expression for the distance between the car and the balloon? So the question that's really being asked is, can we find the expression? And that expression means, can I find that length? That length tells me I need to know what the distance is. And by drawing out the situation, and this is where, once again, the Triforce is very, very beneficial, by drawing out the situation where we know that the balloon is floating along, it floats along parallel to the ground, which means that we end up at a 90-degree angle, which is what creates a situation of having a right triangle, which means that right triangle, we can use the Pythagorean theorem or the distance formula for it. So, again, one of the benefits of this expression is, if I know a certain time, I can plug that time in. This one thing I ask you guys to be careful of are the units. The fact that this is hours means that our time is in hours. So like after 1 hour, you're not going to be plugging in 1 for time. You're going to be plugging in. So after 1 hour, I guess after 1 hour, you are going to be putting in 1. But like if you want to say after 1 minute, you're not going to be putting in 1. You're going to be putting in 1/60th, because it's in terms of hours. All right, section number 1.2. The two big ideas that we want to talk about are symmetry and intercepts. So when it comes to symmetry and intercepts, let's talk about intercepts first. To find the intercepts, what we're going to be doing, pretty straightforward. These are our level 1 style problems. I don't think I identified that. Let me go ahead and identify it right here. So this is a level 1 style problem. To find the intercepts, we basically look to see where it crosses the x-axis and where it crosses the y-axis. Now, algebraically, in order to find the intercepts, to find the x-intercept, we plug in 0 for y and solve for x, which is what I did here. Plugged in 0 for y, and I solved for x. And the reason why is because y equals 0 is the equation of the x-axis, or kind of like what I showed in my notes before. We could write that equation, that y equals 0, as the coordinate x comma 0. And if you look at it as x comma 0, that really translates into what we just did right here. To find the y-intercept, we do the same thing. Now, what happens algebraically if, in this case, we get y squared equals -4? Let me go ahead and take that one step further and say, let me move this first. So let me take that one step further and say y ends up then being plus or minus 2i. Well, plus or minus 2i is not on the real plane, which is why we have no solutions out of this, no real solutions out of this. So there are no y-intercepts that result from it. Problem 2a. 2a, what makes this a little bit more challenging is you end up with some fractional work. Hopefully you could see what I did, where by plugging in the 0, I get 5x equals 7, divide both sides by 5 to get x equals 7/5. Divide both sides for the next expression by -2 to get y equals -7/2. And therefore, we have both of those answers as coordinates. Is this necessarily harder? No, but the answers don't look so nice, which is what a little bit more of a level 2 is, to be comfortable with. Hey, this is a little bit more challenging. Not much, but a little bit more challenging. For part B, what I did, and I'm not sure why this didn't show quite as well. Let me go ahead and move that over. What I like to do, and this is a strategy of mine, that if I have fractions, sometimes I like to just clear the fractions. That way there's less work that I have to do. So to clear the fractions, if I multiply both sides by 12, then I end up clearing the fractions right away. And so then I can solve, where in this case, I will have 9x equals 72, which gives x equals 8. Here I have negative 2y equals 72, so y equals negative 36. For part C, as a level 2 style problem, we end up with a square root of positive 1/3 when you do the when you're solving by square root method. Now, if you remember, and let me go ahead and move the equal sign over, how do we get from point A to point B? How do we get from the square root of 1/3 to the square root of 3/3? Remember, this is the square root of 1 over the square root of 3, and then we could rationalize by multiplying by the square root of 3/3. That's how we get to that value. So, and then to find the x-intercept, let's kind of put a break in there. To find the y-intercept, we plug in 0 for x. Most people don't seem to have issues with that. If you have any questions, please let me know. For this level 3 style problem, to find, I want to use the standard form of the equations to find the intercepts and then sketch a graph. Now, if we remember from algebra 2, if you have an equation like this in standard form, this would be the equation of a line. So that equation of a line, the benefit of standard form is it really does help us find both intercepts correctly. Or more efficiently. I shouldn't have said correctly, but more efficiently. That way, if we plug in 0 for x, 0 for y, we can come up with our answers. For part B, you should know that this is a parabola, and as a parabola, that because we have an x squared and we have a y, we know that when we do the algebra, we come up with x squared is plus or minus 1 and y equals 2. By plotting those points, we should see that this should be the vertex of the parabola. Now, what happens if you don't remember that? What happens if you're like, that doesn't ring a bell? Well, what you can do instead is you can go ahead and do this algebraically to say 2y equals negative 4x squared plus 4. So y is negative 2x squared plus 2. If you remember, this negative 2x squared plus 2, doing translations, this is a vertical shift up 2 and a dilation of 2 reflected over the x-axis. So remember, order of dilations, order of operations for translating is we do our dilation of 2, reflected over the x-axis, then translate it up 2. And that's how we get to that graph. In the end, most students seem to be okay with this, but if you have a question of how to think through that more efficiently, I can talk to you later. For part C, I have a circle centered at negative 2, 1, and the radius of 5, and it does have this equation. So the goal is, let's take the circle, find the intercepts, and sketch the graph. So find the intercepts and sketch the graph. Well, I like to sketch the graph first, and I know that the circle having a radius of 5, that's how I came up with this center, and then each of these points. That doesn't help me find the intercepts, that just helps me generically sketch this graph. So let me go ahead and finish that sketch, by the way. So sketch the graph. To find the actual intercepts, we do the same thing, plug in 0 for y. To find the x-intercepts, plug in 0 for x. What that ends up showing is, or what that ends up giving us is, to find the x-intercepts, we get negative 2 plus or minus 2 squared of 6. Where I find that very interesting is the negative 2 is really going to be the center here. And that distance here is going to be plus this 2 squared of 6. This distance in this direction is going to be minus 2 squared of 6. So we keep that same x coordinate, and then we establish that we're going both ways. And the same thing is going to happen with the y values, that we're going to have this y value of 1, 1 plus a certain number, and 1 minus a certain number, because there should be some symmetry involved. My guess is you should be able to follow through with the algebra of this. If there's any questions, as always, let me know. For problem number 4, and I like these styles of problems, this level 4 problem, because for me, this is which one could fit the situation. I like these problems because they are a lot more open-ended. It's not just one answer. Why do I like that? Because that's really the mathematical thought of what PreCalculus is trying to push. Do you understand how to open your mind a little bit to say, will this fit the situation or not? In fact, mathematical modeling is one of the standards in PreCalculus, and we want to make sure that you can model things appropriately. The correct answer to 4 is A, and we can see that kind of quickly as if you say -3 times 0 plus 2 times y equals 18, that gives you your y-intercept of 9, and then -3x plus 2 times 0 is 18, so the x-intercept is -6. We can see that right here. All right, so plain and simple, that is the answer. Now, what about all the other ones? Are those other ones valid or not valid? I'm going to tell you they're not. But for me, the importance is why not? Why not these? That is the thought process of why would this not work? So if we look at part B, where if we try to find let's go ahead and draw a line right here. So for part B, the x-intercept is -3 and the y-intercept is 4. So let's take a look and say what happens if the x-intercept was -3. That would be -1, -2, -3. That means that our scale should be the same, 1, 2, 3, 4. Unfortunately, that doesn't actually work because our y-intercept is not 4, our y-intercept is 4.5. So the answer to part B almost looks like it's going to work, but in the end, it doesn't. So let me go ahead and erase those. For part C, why doesn't this work? Well, let me go ahead and erase this as well. So for part C, why doesn't this work? Our x-intercept is 3 and our y-intercept is 4. Hopefully you could see that what I'm doing is to find the x-intercept, I'm really just saying where does 4x equal 12? And then I say where does 3y equal 12? Now to have an x-intercept of 3, which would be over on the positive side, this does not have a positive x-axis. This only has a negative x-axis, so I know that that's not correct. And then for this one, this would be an x-intercept of -3 and a y-intercept of 2. So if this is -3, once again, our scale is going to be by 1/2, which means that the y-intercept should be right here at 2. That's not accurate, so not correct. And last but not least, let's take a look at the last one. The x-intercept of this one is a +6 and the y-intercept is a -9. These are the complete opposite of what we want, so that's not correct either. Now, should it be, or what would make it correct? That's actually a stronger form of thought. If this were a -3, then this would be correct. Now, the second half of 1.2. Second half of 1.2 is all about symmetry. If we have symmetry over the x-axis, the main idea is whatever this positive y happens to be, when we reflect it over the x-axis, it becomes the negative of that same y value. Symmetry with respect to the y-axis, whatever this positive x value is becomes this negative x value, and vice versa. Suppose we were starting off at this negative x value. When we have the symmetry, it now becomes a positive x. So, and then last but not least, when we have our origin symmetry is when the positive x reflects to a negative x, the positive y reflects to a negative y. We can see that pretty easily on the graph. And when you take a look at this section, when we're talking about the symmetry of these points, then our main point, which I'm going to call A right here, that main point, if we have symmetry to the x-axis, it takes it down here. If we have symmetry, which means that the y value got negated. Symmetry over the y-axis would take the point over here. That means the +3. Let's go ahead and write that just so you can see that a little bit more. It becomes the -3. Erase that. And last but not least, to have symmetry over the origin, that positive x value of 3 becomes a negative x value. That positive y value of 2 becomes a negative y value, and that's how we show that kind of thing. So what's the only symmetry on here? It's origin symmetry, because if this were y-axis symmetry, we're going to see a graph that sort of does that. This had x-axis symmetry, we're going to see a graph that should have gone down further, but is reflected down there. For the second problem, if a graph has y-intercepts of -1 and 3, so if our y-intercepts are -1 and +3, and we do have x-axis symmetry, what are the other y-intercepts? Well, if it has x-axis symmetry, this point up here would have a matching point down here. This y value would have a matching point right there, so we would now have 4 y-intercepts. So we negate the y values. For part B, if a graph has origin symmetry and we know the largest y value, if we have origin symmetry, then we have the largest y value over here, but the smallest y value over here. And so that if our largest y value is +12, we negate it to have the, if the largest y value is 12, then the smallest y value would be the negative of that, which would be a -12. Now, these level 3 problems are where I see students struggle the most in pre-calculus, or at least for this section. How do we algebraically test to determine if the graph has symmetry? Goes right back again that we plug in, or we substitute -y in for y for the x-axis symmetry. Let's highlight that. We substitute -x in for x for the y-axis symmetry, and then we substitute both in for both. And our goal is if the same equation results, then we have that symmetry. So right here, if you look at 3a, then what you can see that I did for the y-axis symmetry, I wanted to determine the y-axis symmetry, which is why I plugged in -x for x. And when I simplified, I end up with this equation, which is not the same. And why is it not the same? It's because of that minus sign right there. So no y-axis symmetry. For x-axis symmetry, when I substituted -y in for y, once again, I have a negative there, which is not the same, and therefore it's not symmetric to the x-axis. When I plug in both the -x and the -y, the differences that I'm going to highlight are both of those signs, and so they're both, because it's a different equation, we have no origin symmetry. Taking a look at this one, when I plug in -x for x and -y for y in the appropriate spots, here, when I simplify, that ends up being a +5x, not a -5x. For this problem, or for this part of it, if I multiply both sides by -1, that's how I got to that step. Once again, you can see that this is a +5x, not a -5x. Now, when I substitute both in at the same time, once again, if I multiply by -1, down here, what ends up happening is I have the exact same equation that I started with, which means that I have origin symmetry. And last but not least, I just wanted to see, hey, can you remember some different parent functions that you learned in Algebra 2? And I just have a list of the different parent functions. This is not an extensive list, but y equals x looks like that. Y equals x squared, we could see that symmetry. Y equals the absolute value of x, we talked about that one earlier. Y equals x cubed. Y equals x cubed has that basic shape. The cube root function is what's called the inverse. We're going to learn about that this year. And then the square root function doesn't have any symmetry just because we only have a portion of it. It's not over both sides. So if you have any questions, hopefully you liked verbal explanation of all the different things that went on in my notes. If you have any questions, feel free to ask me. And love you guys. I'm looking forward to this year. Have a great day.